Look closely at this waveform. At the micro level, raw financial market data is stochastic. It is a chaotic, erratic system of constant fluctuation. Zooming in to real-time price action reveals heavy pollution from high-frequency volatility. Every tick represents a battle between buyers and sellers, generating immense amounts of random mathematical noise. Buried underneath all of that erratic movement is the signal, the underlying directional macro trend that defines where the asset is going. This chart displays raw tick data. When we consolidate these rapid-fire micro-movements into standardized candlestick periods, we create a raw data baseline. However, even this baseline remains highly volatile, masking the smoother trajectory that dictates actual market shifts. Building a robust systematic trading model requires you to strip away that continuous pollution. You have to mathematically isolate the hidden signal from the noise. In signal processing engineering, there is a tool specifically designed for this problem, the low-pass filter. A low-pass filter operates by attenuating high-frequency noise while allowing low-frequency signals, the structural trends, to pass through. Algorithmic finance applies this exact same engineering concept to price action. This is achieved using three primary time series algorithms: the simple moving average, the exponential moving average, and the displaced moving average. These algorithms function as rigid mathematical protocols, dictating exactly how historical data is weighted and processed. Translating raw data into an actionable quantitative system requires a strict understanding of the underlying calculus of these three filters. The simple moving average, or SMA, is an unweighted arithmetic mean calculated over a specific number of periods, designated as n. The formula requires a strictly defined look-back window, pulling a sequential series of closing prices. On this chart, we have an isolated 20-period look-back window. The calculation is straightforward. We sum the closing prices of these exact 20 periods and divide the total by 20. The defining operational mechanic of the SMA is its distribution of weight. As shown below the price data, the formula assigns the same mathematical importance to the price 20 days ago as it does to the price today. By rolling this calculation forward one period at a time, we plot a continuous line against the price action. This equal distribution of weight excels at neutralizing erratic microvolatility, producing a smooth structural baseline that reflects the macro environment. That absolute smoothness introduces the SMA's critical vulnerability, severe latency. Consider a sudden volatility gap. Right here at the current time, T0, the asset experiences a violent upward price shock. The SMA line barely registers the event. The N-1 historical data points mathematically anchor the average down, heavily diluting the impact of the new shock. The indicator recognizes the regime change far too late to be actionable. By the time the arithmetic mean pulls the line high enough to signal a shift, the move is often already complete. The SMA is exceptionally smooth, but its inherent latency makes it a dangerous tool for models requiring rapid reactivity to market shocks. The exponential moving average, or EMA, acts as the quantitative solution to SMA latency. To fix the lag, we stop treating all historical data equally and assign mathematical priority to recency. This requires a weighting multiplier, designated as alpha. We calculate alpha by taking 2 and dividing it by our look-back window, n plus 1. This multiplier replaces the equal distribution with an exponentially decaying curve of importance. The data at T0 receives the heaviest weight, while the significance of past data asymptotically shrinks toward 0. The formula is recursive. Today's value explicitly relies on the calculation of yesterday's EMA, ensuring all past price history is mathematically embedded, even as its weight decays. Decaying weight, the EMA successfully captures momentum and structural shifts significantly faster than an arithmetic mean. Apply the same sudden price shock from before, and the difference is immediate. The EMA turns sharply upward, moving in near lockstep with the single new candle. Where the SMA diluted the shock, the EMA reacts to it almost instantly. But that speed comes with a severe trade-off. Extreme recency bias makes the EMA highly susceptible to isolated noise. It treats random, transient volatility spikes as legitimate trend shifts. This creates a whipsaw event. A short-term noise spike pulls the sensitive EMA line into generating a false positive, only to revert to its mean. The EMA trades latency for a significantly higher risk of false positives. A mathematically faster indicator is not superior. It simply prioritizes reactivity over stability. We have altered how data is weighted. Now we manipulate the temporal axis itself. This brings us to the third mechanism, the displaced moving average, or DMA. By definition, a DMA is simply a standard simple or exponential moving average whose plotted coordinates have been shifted horizontally forward or backward by a set number of periods, k. Here we displace the entire line 5 periods into the future. Shifting the axis forward projects a historical baseline ahead of the current price. We use this empty space to anticipate future support or resistance intersections before the price action actually arrives there. Conversely, shifting the axis backward aligns historical indicator signals directly over past price shifts, allowing quants to audit the exact validity of a trend change against a delayed baseline. This spatial shift entirely decouples the low-pass filter from being locked to the current T0 moment. The DMA transforms a purely reactive smoothing line into a structural framework used specifically for spatial and temporal alignment testing. Here are 3 identical, highly volatile price charts mapped with our distinct filters. In Panel 1, the SMA maximizes structural smoothness at the cost of actionable latency. In Panel 2, the EMA minimizes latency while inheriting high exposure to noise. In Panel 3, the DMA abandons reactivity, manipulating time to test structural alignment. This illustrates the overarching theorem of time series analysis. There is no flawless, omnipotent indicator, only calculated mathematical trade-offs between latency and smoothing. Professional institutional models do not search for a best indicator. They carefully match the specific mathematical properties of an algorithmic filter to a precise objective. The sluggish, equal-weight SMA is routinely deployed to establish macro baselines, while the hypersensitive EMA is strictly reserved for reactive momentum triggers. Common retail assumptions regarding indicator superiority usually stem from a fundamental misunderstanding of their underlying calculus. The primary goal of quantitative system engineering is to apply precise low-pass filters to isolate objective, actionable truth from the daily chaos of market noise. Algorithmic edge is defined by a mastery of the mathematics beneath the line.